All right, this next problem is a bit on the long side. I'm just going to warn you now. All right, suppose liquid is pouring through a cone-shaped filter that has a radius of 4 inches and a height of 16 inches. So I'm just going to stop right there. Cone-shaped filter, so it's probably open at the top because we're pouring something into it, and then I've got the cone coming down, okay? And what I know about that cone is the radius up here is 4 inches. Actually, I'm not even going to write r equals. I'm just going to write 4 inches. And the height, vertical, is 16 inches. All right? Since that's the size of the actual filter, none of those numbers are changing. Okay? Those are fixed values. Now, if the liquid is flowing out at 2 cubic inches per minute, so that means there's liquid coming out of this thing. And see how it says cubic inches per minute? Cubic inches means I'm talking about a volume. So this is dV dt is 2 cubic inches per minute. And it's coming out. So that means if I look at the liquid level inside, it's going down because liquid is flowing out. So this is a negative rate of change. Okay, negative rate of change. The question is, how fast is the depth of the liquid changing? Okay, so let me start drawing a different color here. How fast is this depth or this height changing? So I'm going to draw radius and height when the level is 8 inches deep. So I'm going to call this R because that's going to be a changing radius, because as the liquid level goes down and down and down, the radius gets smaller and smaller. Okay, so that's a changing R. I'm going to call this H for height, just so I can stick with what's the formula for the volume of a cone. You could call it D for depth if you prefer, but I'm going to stick with H. All right, the question is asking me, what is dH dt when the height is going to be 8 inches? Okay, there's a lot going on there, but here are my key things. I know radii, I know heights, and I know volume rate of change. So I need a volume equation here. So the volume of a cone is equal to 1/3 pi r squared h. Okay, 1/3 pi r squared h. Now the problem with this is I've got too many variables. If I've got both r squared and h in there, when I do the derivative, I would need product rule and I would have dr dt and dh dt, two unknowns, and that's too many unknowns. I can only have one unknown. So what I need to do is I need to rewrite this in terms of a single variable, and I know for a fact that you guys did this in honors pre-calc. So let's revisit how that works. We basically have similar triangles here. We've got the orange triangle over here with H and R. And then if I take another look at this, let me do it with a highlighter so it's slightly, you can see. There's another triangle here that is a fixed ratio. Okay, that one's a fixed ratio. So now how do I make this work? All right, my similar triangles, I'm going to do them in blue. And this is going to happen on every cone problem. And you're going to have a few cone problems to deal with. So get ready, guys. It's coming. All right, the big one has a radius of 4 and a height of 16. The little one, which is changing, has a radius of r, an unknown number, and h, an unknown number. So I can set up a ratio between those. I could do 4/16 equals r/h. I could do 4/r equals 16/h. I can set up the proportion any way that I want as long as it's consistent between the two fractions, okay? So I'm doing radius over height equals radius over height. Now I'm looking for dH dt, which means this h needs to stay and this needs to go. We need r to go away. Rain, go away. All right, so I'm going to take this proportion and rewrite it so it says r equals. Well, 4/16 is 1/4. I'm not writing a 4, sorry. And then move the h to the other side by multiplying. The radius is equal to 1/4 the height. So what I can do is I can take the equation up here. I know it's getting a little jumbled. I'm going to go on to the next slide in a minute. I've got the volume is equal to 1/3 pi. The radius is now 1/4 of the height. Square that, and then I have the other h. Okay, there's substitution involved. So what I'm going to do now is I'm going to simplify this as much as humanly possible. So I'm going to get volume equals 1/3 pi. If I square this, I'm going to get 1/16 h squared times h. The 1/3 and the 1/16, that can merge down into 1/48. Then I've got the pi, and then h squared times h is h cubed. This is the equation I want to work with. Now keep in mind, I haven't done a lick of calculus yet. This is all algebra and pre-calc in front of me, and a little bit of geometry too, all right? It's a little bit downhill from here though, because this is a much more straightforward function to take the derivative of, because one side has one variable, the other side has a single variable. So I'm going to copy that equation down. I've got volume equals 1/48 pi h cubed, and I'm going to do the derivative now. Okay, so the derivative of that, dv dt, is equal to 3 times 1/48, 3/48, which I can reduce down to 1/16 pi. The derivative of h cubed is h squared, and then times dh dt, which is in fact what I'm looking for. And now the beautiful thing is, I know dv dt, it's right here. There's dv dt. All right, so I've got -2 is equal to, I'm going to reduce that 3/48 down to the 1/16 that I mentioned before. And then h, if I go back up for a moment here, we had right here that we wanted h to equal 8 after we do the derivative. So I'm going to plug in an 8. And then dh dt. And now I want to solve. All right, so here we go. Cleaning up the right-hand side, I've got -2 on the left. 8 squared is 64. 64 times 1/16 is just a plain old 4. Divide over, and you're going to get dh dt is equal to -2 over 4 pi. Okay, that's an exact value answer. The rate of change of the height, let's see, back at the beginning we were talking about cubic inches per minute, so this is going to be a linear distance, inches per minute. Or if you go with a decimal, decimals are fine, as long as you're careful with them. When you type this into a calculator, you need to put parentheses around that, okay? And we're going to end up with -0.1592. It's going to keep going, I think. So we're going to get -0.159 inches per minute. And yes, I know in class I said that we should write the whole thing out, but I'm sorry, I'm going off with some old notes and we used to always round. So it's okay to write out the whole decimal. It's okay to round to 3 decimal places. It's okay to truncate to 3 decimal places. It's okay to give an exact value answer. They're all good. So you can give this answer right here. Yes, you could reduce that to -1/2 pi if you prefer. You don't have to, though. They'll take it because it is correct mathematics, all right? That's how you deal with a cone. They're lots of fun. Send no one ever. All right, guys, one more to go.